All right, this is waves 4. So let's start doing the first harmonics for a tube that is open at both ends. We want the wavelength and frequency for each one. I didn't put it on the worksheet, but what we need to go ahead and do is assume that the velocity of sound for this whole thing is 343 meters per second. That's going to help when we're making the calculations, but that's really the only thing that's going to help. So for a tube that's opened at both ends, in order for a standing wave to form, that tells me that I have to have an antinode at each end. So the only wave shapes that are going to fit into a tube that is open at both ends are wave shapes that have antinodes at both ends. So it's open at each end. So our standing wave is going to look like that. This would be the first harmonic. So let's go through the whole thing. This length is L, and this is only half of a wave. So if we look at this, this is half of a wave. The whole wave would come back down and stop right there. So because we only have half of a wave, what we're going to say is that L is equal to 1/2 lambda. And so if we solve that for lambda, the wavelength is equal to 2L. Since L is 2.5 meters, the wavelength is equal to 5 meters. That's the biggest wave I can put on here. Now that we have the wavelength, the frequency is going to be the velocity divided by the wavelength. So 343 meters per second divided by 5 meters. That gives me a frequency of, sorry about that. Gives me a frequency of 68.6 hertz. So that's the process that we're going to go through for all of this. So let's look at the next one. We're going to have the same length pipe because it is the same pipe. We're going to move up to the next harmonic, which means we're going to try to fit one more half wave in here. So I'm going to get an additional node. Now I've got a full wave on the inside. This is n equals 2. And since I have a full wave inside of L, L is equal to lambda, which makes this next part easy. Lambda is equal to 2.5 meters. And the frequency is going to be the velocity, 343 meters per second, divided by 2.5 meters. When you put that in your calculator, you get 137.2 hertz. For the next shape, we have the same length L, but we're again fitting more of a wave in there. So the next more that we can put in and still meet our boundary conditions for the standing wave is going to have, at this point, 3. Going to have 3 antinodes. So same kind of shape. But at this point, we had 1, 2, 3 antinodes up here. We're going to have 1, 2, 3, 4 antinodes up here. N equals 3. And if we look at it, that's one wave. So we have 1.5 waves. So inside of this length, I have 3/2 of a wave, meaning my wavelength is 2/3 L. And so when we plug that in and we calculate it, that makes L 1.66 meters. I believe. I want to make sure on that. Yep, 1.66 meters. The frequency again, 343 meters per second divided by 2.5 meters. That gives me a frequency of 205.8 hertz. I hope you're starting to see a little bit of a pattern that we have going on here. For the next one, it's the same length, it's the same object, but we're going to be fitting even more of a wave on it. So if we had if we had 3 nodes, we're now going to have 4. So our wave shape looks like that. I've added an additional antinode. I've added an additional half a wave. So now I have 4 halves of a wave. That means that my wavelength is 2/4 or 1/2 of the length that we're given. So the wavelength here is 1.25 meters. And then my frequency is 343 meters per second divided by 2.5 meters. Sorry, not 2.5. 1.25 meters. We'll put that in, and it's 274.4 hertz. Now, while we're here, let's talk about some patterns that we notice. So, every time we move on to the next harmonic, we are adding half a wave, right? So we start off with half of a wave. The next thing we get is 2 halves of a wave. The next thing we get is 3 halves of the wave. The last thing we get is 4 halves of a wave. If we were to come up with an in general pattern for this, and this is something that we've done on previous work, if we were to come up with an in general pattern for this, we would say that the length is equal to n lambda over 2, and if we solve that for the wavelength, that's the length of the pipe. If we solve that for the wavelength, the length of the wave is 2L over n is 2L over n, where n is the number of harmonics I have. That's the first little pattern that we see. The second pattern, if we look at the fundamental frequency, this is the lowest frequency that we can get to resonate, or the lowest frequency that we can get to set up a standing wave in our object. So, if we follow that, coming down to the n equals 2, that's twice my fundamental frequency. Over here to the n equals 3, that's 3 times my fundamental frequency. And this is 4 times my fundamental frequency. So the frequency at a given harmonic, f sub n, is equal to the number of harmonic times the fundamental frequency. You go to a different harmonic, you are that many multiples above the fundamental frequency. All right, let's look at the 2 meter long tube that's only open at one end. So for a 2 meter long tube only open at one end, it's a different length. That's going to change some stuff. But if it's only open at one end, that gives me some conditions that must be met. We have a node at a closed end, and we have an antinode at the open end. So the first shape that I can fit in here has a node at the closed end and an antinode at the open end. Well, the simplest thing is just this. Now, how much of a wave is this? Well, a full wave would go down and come right back up. So this shape that we see, it's not a great drawing of a full wave, this shape that we see is only 1/4 of a wave. All right, so for n equals 1, inside of my length L, I have 1/4 of a wave. That means that the wavelength is equal to 4 times L. So in this case, my wavelength is equal to 8 meters. And then if I want the frequency, again, I'm going to take the speed of sound, 343 divided by 8. I get 42.9 hertz. Easy enough. So let's look at the next shape that we can do. Now, as always, when we're moving to the next possible harmonic, we're going to add half of a wave, or we're going to add one node. And in order for that to happen, node here, anti-node at the opening. So if we're counting how much of a wave we have, each shape like this is a quarter of a wave, and I have 3 of them. So that means I have 3/4 of a wave. So the length is equal to 3/4 of a wave. That means I skipped n equals 2 and I jumped up to n equals 3. We have to remember that for something closed at one end, the only harmonics that meet our little boundary conditions here are odd ones. So we skipped 2 because it's not a possibility. Because I didn't just double my shape, I tripled it. So if we take that, that's going to be lambda. Oh, sorry. So now 4L over 3 is equal to my wavelength. And that makes my wavelength 2.66 meters. And then if we solve for the frequency, that's 343 meters per second divided by 2.66 meters, or 128.6 hertz. Next one, again, in order for this to work, we're going to add another half of a wave because it meets our boundary conditions. So we're adding another node. Sorry, we're adding another node because it's another anti-node in there. And again, counting quarters of a wave, we have 1, 2, 3, 4, 5 quarters of a wave. N equals 5. And so inside of my length, I have 5 quarters of a wave. That means that 4L over 5 is equal to my wavelength. Plug in 2 for that, and my wavelength comes out to be 1.6 meters. And then my frequency is 343 divided by 1.6, and my frequency comes out to be 214.4 hertz. Clean that up a little bit. Okay, the next harmonic is going to be odd, so that means it's going to be n equals 7. So we're going up by odd numbers. We're adding another antinode and another node. There we go. That's n equals 7. And if we count it, we have 1, 2, 3, 4, 5, 6, 7 quarters of a wave. So inside my length L, I have 7 quarters of one wavelength, which means that one wavelength is going to be 4 times L over 7, making that one wavelength come out to be 1.14 meters. And then when we solve for our frequency, 343 meters per second divided by 1.14, that's 300.8 hertz. I like to do the same thing and kind of look at some patterns. As we're looking at patterns that we see, apologies there, every time we add another harmonic, so as we go from 1 to 3 to 5 to 7, we're going from 1 quarter of a wave to 3 quarters of a wave to 5 quarters of a wave to 7 quarters of a wave. So that tells me that if we want to do this in terms of harmonic, it's going to be the number of harmonic divided by 4 times lambda, with a caveat that we only have odd ends. And then if we take that and we solve for lambda, we start off with 4L over 3, then it's 4L over 5, then it's 4L over 7. So, on a little pattern here, lambda would be equal to 4L over the number of harmonic. And again, only odd numbers of harmonic. And here is my favorite one. This is my fundamental frequency. This is 3 times my fundamental frequency, 5 times my fundamental frequency, 7 times my fundamental frequency. So just like we had up there, the frequency of any harmonic is that harmonic times the fundamental frequency. But we only have all odd harmonics here. All right, so some multiple choice questions. A rope of length L is clamped at both ends. Which one of the following is not a possible wavelength for standing waves on this rope? Okay, so if it's clamped at both ends, that means I have nodes at each end. So the biggest thing I can put on here, so if this is my length L, so the biggest wave that I can put on here is this shape. The longest wavelength that I can put on here is this shape. So this is only half a wave. Half of a wave is equal to L. So lambda is 2L. That's my biggest wave. So I can get 2L. L would be the next one. This would be the next one. This would be the next one. All of those are possible. 4L is not. That's too big. I will never have a wavelength that's 4 times that length. We have another one that's clamped at both ends. It's vibrating at 200 hertz and it resonates in 6 segments. I want to know the speed of the waves. Speed is frequency times wavelength. So I know the frequency is 200 hertz. What I need is the wavelength. If I have 6 segments, each segment, each bump, is half of a wave. So there are 3 waves on this string. If that's the case, one wavelength is equal to, 3 wavelengths on the 4 meter long string. One wavelength is equal to 4/3, or 1.33 meters. So the velocity is 200 hertz times 1.33 meters. So 1.33 meters times 200 hertz is 267 meters per second. Another string, again clamped at both ends, vibrates in 7 segments at a frequency of 240 hertz. What frequency will cause it to vibrate in 4 segments? So 7 segments is n equals 7. So we know that the fundamental frequency, so we know that the frequency at 7 is equal to n times the fundamental frequency. So 7 times the fundamental frequency. So the frequency at 7 is 240 hertz. That's equal to 7 times the fundamental frequency. That makes my fundamental frequency 34.29 hertz. That's my fundamental frequency. And they're asking about what's going on when we vibrate in 4 segments. Well, that's n equals 4. So the frequency at 4 is 4 times the fundamental frequency. So 4 times 34.29 hertz. That makes the frequency with 4 segments, or on the 4th harmonic, 137.14 hertz. So closest to 137 hertz. All right, so we have 2 pipes. Pipe A is 0.5 meters long and open at both ends. Pipe B is open at one end and closed at the other. We don't know how long pipe B is. Determine the length of B so that it has the same fundamental frequency as A. It was tough. Okay, so we're open at both ends. The fundamental frequency when we're open at both ends corresponds to half of a wave. That looks like that. So lambda over 2 is equal to 0.5 meters, and that wavelength is equal to 1 meter. So the wavelength for the fundamental frequency is 1 meter. So for B, the fundamental frequency has a wavelength that looks like this. So for the fundamental frequency, I have 1/4 of a wave is equal to the length of that 2 for my fundamental frequency. Now if I want it to be the same fundamental frequency, it's going to have the same fundamental wavelength. So 1 meter over 4 is equal to that length. That length is going to be 0.25 meters. That would be the same shape that I could fit on there. And then number 5, determine the shortest length of pipe open at both ends, which will resonate at 256 hertz. So, speed of sound is 343. For this shortest length of pipe at 256 hertz, we're looking for the fundamental frequency again. So, half of a wavelength fits into my pipe. That means I need to find my wavelength in order to find L. So, lambda is velocity over frequency, 343 meters per second divided by 256 hertz. So my wavelength is 1.33 meters. So I want my shortest length of pipe. I need a fraction of a wave, because if I continue to go up, I get lambda equal to L, I get 3 lambda over 2 equal to L, I get 4 lambda over 2 equal to L. Each one of these things is bigger than the fundamental. Fundamental is my shortest length of pipe for a given wave. So if lambda over 2 is L, then it's 1.33 divided by 2 equal to my length. My length comes out to be 0.67 meters.